Welcome to the Sleepless Universe. In this journey, we will travel billions and even trillions of years into the future, exploring how the universe will change as time flows on. From the subtle drifting of stars to the final fading of light itself, we will witness every stage of cosmic evolution. Before we begin, tell me in the comments where you're watching from and what time it is for you right now. If you enjoy this kind of content, I'd be grateful if you left a like and subscribed, so you'll never miss another trip through space and time. Now, find a comfortable spot, relax, and let's drift into the far future together. The universe after 1 million years. 1 million years into the future might sound almost unimaginably distant when measured against a human lifespan. Yet, in the grand scale of cosmic time, it is the blink of an eye. From the universe's perspective, 1 million years is a small ripple in an ocean that stretches across billions upon billions of years. The changes that will occur over such a span will be subtle in some respects, dramatic in others, and they will be written in the slow, deliberate handwriting of astrophysics rather than the hurried script of human history. The first thing to understand about the universe after 1 million years is that the stars we see in the sky today will have subtly but unmistakably changed position. Our constellations, the familiar patterns humans have used for navigation, myth-making, and storytelling, will be warped almost beyond recognition. This shift is caused by what astronomers call proper motion, the slow drift of stars across the sky as they orbit the center of the galaxy. Even the seemingly fixed points of light are not fixed at all. They are racing through space at speeds of tens or hundreds of kilometers per second. Over thousands of years, the effect is minimal, but in 1 million years, the change becomes so significant that none of the constellations we know today will survive intact. For any intelligent observers alive at that time, whether human descendants or entirely different beings, the night sky will be alien. Some bright stars like Sirius or Vega may have moved to entirely new neighborhoods, while others will have drifted beyond visibility. New stars will take their place in the firmament, glowing like unfamiliar jewels. The Milky Way's dust lanes will still arc across the sky, but the patterns within them will shimmer with subtle differences. The Sun, our own life-giving star, will be almost indistinguishable from the one we know today, at least to the naked eye. Its life cycle is measured in billions of years, so a million-year interval changes it only slightly. However, subtle is not the same as negligible. Deep within its core, the slow conversion of hydrogen into helium will have shifted the balance of forces just enough for the Sun to grow imperceptibly brighter, about 1% more luminous than today. That may sound trivial, but even such a small increase in solar output can have long-term effects on Earth's climate. Geologically, Earth will not be frozen in time either. The slow drift of tectonic plates will have subtly altered the continent's outlines. The Atlantic Ocean will have widened further as the Americas drift away from Europe and Africa. The Mediterranean Sea may shrink or close entirely if Africa continues to push northward into Europe. Meanwhile, mountain ranges like the Himalayas will be taller, while erosion will have reshaped others into softer forms. Volcanoes will rise and fall. Somewhere on the planet, an eruption as massive as any in recorded history will have altered weather patterns for years or decades, sending ripples through the biosphere. In this future Earth, species will have come and gone. 1 million years is long enough for evolution to sculpt entirely new forms of life, especially in isolated regions. If humans or their descendants remain, they may look the same, or they may be unrecognizably adapted to whatever environments they inhabit. Evolution is opportunistic, driven by survival rather than sentiment. And if our descendants live in domed cities on the moon or beneath the oceans, their bodies may have changed in ways we cannot predict. Astronomically, the solar system will remain stable in its architecture, but it will not be untouched. The orbits of planets are not perfectly fixed. Gravitational nudges from one another, as well as from passing stars or rogue objects, can subtly alter their paths over long stretches of time. In 1 million years, the changes would be measurable but small. Still, some comets currently on long, slow journeys toward the inner solar system will have arrived, perhaps delivering ice to the outer planets or crashing spectacularly into the Sun. Perhaps the most striking visible difference to any skywatcher in this era will be the supernova remnants and new stellar phenomena scattered across the sky. Massive stars have short lives, just millions of years long, and in the coming million years, several stars within a few hundred light years of us are destined to explode. The red supergiant Betelgeuse, for instance, could go supernova at any moment in astronomical terms, whether that is tomorrow or hundreds of thousands of years from now. When it does, it will outshine the moon for weeks and leave behind a glowing cloud of debris visible for centuries. In the broader galaxy, 1 million years will see subtle rearrangements of the spiral arms' structure. Star-forming regions will shift and evolve. The Orion Arm, where our solar system resides, will continue to drift around the Milky Way's core, carrying us toward regions of space that look different in every wavelength of light. Gas clouds will collapse into new stars, and old stars will die quietly or violently, scattering heavy elements that may one day form planets. Life beyond Earth, if it exists, will continue its own path of change. Civilizations, if they arise elsewhere, might rise and fall in time spans far shorter than 1 million years. Others might endure, leaving behind technological footprints that drift through space. 1 million years from now, the faint radio signals humanity has been sending into the cosmos for just over a century will have traveled a sphere 1,000 light years in radius, brushing against thousands of stars and their planetary systems. Any reply from a civilization at that distance would still be on its way back. In this distant yet still young future, the universe is very much alive. Stars are being born, galaxies are bright and active, black holes feed on surrounding matter, and light from the earliest galaxies is still reaching us. The vast, cold darkness of deep time has not yet arrived. Instead, this is a period of quiet transition, where the seeds of far greater changes are being sown invisibly, waiting to unfold over tens or hundreds of millions of years. The universe after 1 million years is not an endpoint. It is merely the first step on a journey toward transformation so vast, they make even this span seem fleeting. And for any beings who look up at the sky then, the constellations they know will be theirs alone, unique to their time in history, destined to vanish into the shifting tapestry of the stars. If we could stand on Earth 1 million years from now, the air might feel different, not because it is unbreathable, but because the composition will have subtly shifted. Over such timescales, carbon cycles, volcanic activity, and perhaps the influence of intelligent life will alter the balance of gases. Oxygen levels could be slightly higher or lower depending on the state of plant life and oceanic ecosystems. Tiny changes in greenhouse gases could nudge climate patterns in ways that influence everything from rainfall to the spread of deserts. The planet's tilt in orbit will also vary slightly due to gravitational interactions with the Moon and other planets, subtly changing the rhythm of seasons and ice ages. Speaking of the Moon, in 1 million years it will have drifted farther away from Earth by roughly 3.8 centimeters each year, amounting to nearly 38 kilometers of extra distance. This separation will weaken its gravitational influence, making tides a little gentler and shortening the length of total solar eclipses. Our satellite will still dominate the night sky, but its apparent size will be ever so slightly smaller. Over unimaginably long stretches of time, it will move far enough away that perfect eclipses will no longer occur. But 1 million years is only a small step along that path. One might expect that, given such a long stretch of time, humanity, or whatever replaces us, would have spread far beyond Earth. Even if our species does not achieve interstellar travel, colonization within the solar system is a distinct possibility. In 1 million years, any surviving civilization could have permanent settlements on Mars, in the asteroid belt, or even on moons like Europa and Titan. These worlds, inhospitable in their natural state, might be transformed through technology into places capable of supporting life, either through terraforming or enclosed habitats. Over 1 million years, cultures, languages, and genetic adaptations could diverge dramatically between planetary colonies, producing new branches of humanity. However, the possibility also exists that Earth could be empty of intelligent life by then. Civilizations rise and fall in time frames measured in centuries or millennia, and even the longest-lived human empires have lasted only fractions of the time we are discussing. Whether through natural disasters, self-inflicted catastrophes, or slow decline, intelligent species can vanish, leaving behind ruins that erode into the landscape. In such a case, 1,000,000 years from now, the only traces of our existence might be the most durable of our creations: radioactive isotopes in the rocks, bits of spacecraft on the moon, or strange alloys that resist corrosion for millions of years. Farther afield, our cosmic neighborhood will see the arrival of a few wandering stars. The Milky Way is not a static place. Its stars orbit the galactic center in different directions and at different speeds, meaning close encounters are inevitable over long timescales. In about 1.3 million years, the star Gliese 710 is expected to pass within just 1.3 light-years of the Sun, close enough to disturb the Oort cloud, a vast sphere of icy bodies at the edge of our solar system. Such a disturbance could send a cascade of comets inward, potentially leading to spectacular night skies or even dangerous impacts on planets. By 1,000,000 years from now, other stellar visitors may have brushed past, subtly altering the orbits of distant debris and sprinkling the inner solar system with icy interlopers. For observers in that era, astronomy will still be a discipline of light and patience. Yet their telescopes, whether optical, radio, or built on principles we have not yet discovered, may reveal details about the universe far beyond our current grasp. They may directly image Earth-like planets around other stars, with the clarity we see our own moon today. They may detect the atmospheric signatures of life light years away. They may even observe the earliest moments of the universe with such precision that the cosmic dark ages, the epoch before the first stars ignited, becomes as well mapped as our current skies. The Milky Way itself will still be largely the same galaxy, with its graceful spiral arms and bright central bulge, but change will be underway. The slow gravitational dance between the Milky Way and the Andromeda Galaxy will still be in its early stages, but Andromeda will be closer, larger, and more prominent in the sky, perhaps a visible hazy smudge to the unaided eye even in areas where light pollution exists. This looming approach will eventually lead to a collision in 4 billion years, but in 1,000,000 years it will still be only a subtle hint of things to come. On the scale of life and biology, the changes in 1,000,000 years could be astonishing. New apex predators could roam the continents. Insects could evolve entirely new wing shapes or social behaviors. Birds might take on strange new forms, or entirely new classes of organisms might appear, arising from evolutionary experiments driven by climate change, continental drift, and genetic mutations. If humanity is still here, we may look back at our own evolutionary history in awe, tracing the arc from Homo sapiens through stages of technological and perhaps even biological transformation that blur the line between organism and machine. Even the deep oceans will evolve in ways not immediately visible to surface dwellers. Currents will shift as continental positions and climate change alter the great conveyor belts of water that distribute heat and nutrients across the globe. Deep-sea ecosystems will adapt to new conditions, perhaps flourishing in places that are today barren and collapsing in places that now teem with life. Coral reefs may have vanished or been replaced by entirely different forms of oceanic architecture built by other organisms. The human imagination struggles with such immense spans of time because we tend to anchor ourselves in personal and cultural memories. But the truth is that 1,000,000 years is still just a prologue in the universe's grand story. Stars will continue their nuclear burning, galaxies will continue to rotate, and the cosmic background radiation will still whisper the faint echo of the Big Bang. For all the changes on the surface of our tiny world, the deep rhythm of the cosmos will remain unbroken. 1,000,000 years from now, the night sky will tell a different story than the one we know today. The constellations will be strangers, the moon a slightly more distant companion, the sun subtly brighter, and the earth a world reshaped by both nature and the hand of life. Whether the storytellers of that age are human, alien, or none at all, the universe will still be a place of endless transformation, waiting for the next chapter to be written. 10 million years in the future. 10 million years is a vast gulf compared to human history. Yet in the context of the cosmos, it is still just a flicker. Even so, by this point, the cumulative effects of geology, biology, and celestial motion will have reshaped the Earth and the sky in ways that are unmistakable. The familiar landmarks of our present age, both on land and in the heavens, will have been transformed into something almost unrecognizable. The constellations we know today will have been gone for millions of years, replaced by entirely new patterns formed by the relentless proper motion of the stars. Every single point of light in the sky will have shifted to a new location, weaving together constellations that no culture in our time has named. These shapes will belong entirely to the beings alive then, each one rooted in their own myths, stories, and interpretations of the cosmos. Bright stars like Sirius and Procyon may no longer shine in our skies at all, having drifted beyond visibility or burned out entirely. New stellar neighbors, once invisible to us, will blaze brightly in their place. One of the most profound astronomical events likely to occur in this span is the appearance of new supernova remnants scattered across the galaxy. Several massive stars relatively close to the solar system are on track to end their lives in violent explosions within the next few million years. Betelgeuse may have long since erupted, leaving behind a glowing nebula and a neutron star or black hole at its core. Other giants, perhaps stars we cannot even see yet, will have joined it, lighting up the skies of the future with brief but spectacular displays. The shockwaves from such explosions will ripple through space, compressing clouds of gas and dust into new generations of stars, ensuring that the cycle of stellar life and death continues. The sun will still be in the prime of its life 10 million years from now, but it will be slightly more luminous, its steady fusion of hydrogen into helium increasing its output by a few percent compared to today. This subtle shift will have consequences for Earth's climate. Global temperatures will be slightly higher, potentially accelerating natural climate cycles and altering rainfall patterns. Ice sheets at the poles, if they still exist, will have expanded or retreated in rhythm with these cycles, leaving behind geological scars that tell the story of shifting climates over millions of years. Tectonic plate movement will have completely redrawn the map of Earth. Africa's slow but steady march northward will have brought it into a collision with Europe, closing the Mediterranean Sea entirely and pushing up new mountain ranges where southern Europe once lay. The Atlantic Ocean will have widened considerably, placing the Americas even farther from Europe and Africa. New seaways may have opened between continents, while others have closed. Volcanoes will have erupted countless times, shaping new islands and destroying others. In some regions, entire coastlines will have been drowned by rising seas, while elsewhere, land will have emerged from the ocean to create new habitats for life. Over such a span of time, evolution will work profound changes on life itself. Species that dominate today may be long extinct, replaced by new forms better adapted to the climates and environments of the future. Predators and prey will have co-evolved into new balances, with entirely new ecological niches emerging. If humans or their descendants survive, they may have physically changed as well, perhaps subtly, perhaps drastically. Cultural evolution will also have marched on, shaping languages, technologies, and social structures beyond recognition. The moon will continue its slow retreat from Earth, now tens of thousands of kilometers farther away than in our time. This will make total solar eclipses rarer and shorter, and the moon will appear noticeably smaller in the sky. Tides will be weaker, subtly influencing coastal ecosystems and the movement of nutrients in the oceans. Over millions of years, these changes will ripple through the web of life, altering migration patterns and the structure of food chains. Far beyond our solar system, the Milky Way will continue its graceful rotation, carrying the sun and its planets into entirely new regions of space. The solar system's neighborhood will look nothing like it does today. We will have passed close to other stars, perhaps altering the orbits of distant icy bodies in the Oort cloud and sending comets tumbling inward. The long, slow gravitational waltz between the Milky Way and Andromeda will have brought our neighboring galaxy even closer, making it a bright and undeniable feature in the night sky. If humanity has reached a level of technological advancement sufficient to spread across the galaxy, the 10 million year mark could see us, or our successors, established on countless worlds. Civilizations could be scattered like seeds across the spiral arms, linked by communication networks operating on timescales incomprehensible to our present minds. Alternatively, humanity could have vanished entirely, leaving only silent ruins on Earth and other planets, monuments to a species that once reached for the stars. Technological artifacts built to last millions of years could still endure. Probes sent into interstellar space might still be drifting, carrying messages to whoever or whatever finds them. Structures carved into stable geological formations might still bear traces of their makers. If any intelligent observers exist, they may study these relics as archaeologists of deep time, piecing together the story of a civilization that lived in what they might call the early days of the galaxy. Meanwhile, the physical universe will still be vibrant and active. Stars will be forming in vast nurseries of gas and dust. Black holes will be devouring matter, emitting powerful jets of energy that can be seen across millions of light years. Planets will be coalescing around young stars, while others will be torn apart by gravitational forces or consumed by their suns. In the scale of cosmic history, this will still be an age of light and creation, far from the deep, cold future when the stars themselves will go dark. One of the most striking features of Earth after 10 million years will be the complete erasure of any surface traces of our present-day cities and infrastructure. The combined effects of erosion, vegetation growth, shifting tectonic plates, and sedimentation will have buried or obliterated most of what humans have built. Even the tallest skyscrapers will have collapsed and been reduced to rubble, with only faint imprints remaining beneath layers of soil and rock. The only exceptions might be a handful of structures intentionally designed to last geological timescales, monuments carved into mountains, or artifacts stored deep in stable rock formations. Yet even these could be altered by earthquakes, floods, and volcanic activity. This impermanence is not unique to human creations. It is a fundamental truth of the Earth itself. Continents will not resemble their current forms. Vast deserts may cover regions that are now lush forests, while fertile plains may bloom where oceans once stood. Glaciers may advance and retreat multiple times, leaving behind moraines and reshaped valleys. New mountain ranges will rise, some destined to rival the Himalayas in height, only to be worn down over millions of years by wind and water. Ocean currents, which regulate global climate, will have shifted significantly due to changes in continental positions and sea levels. These currents drive the distribution of heat and nutrients around the globe, meaning their alteration could have major consequences for the biosphere. Entire ecosystems may migrate or disappear as the oceans reorganize themselves. Coral reefs, if they still exist, might have evolved into entirely different forms, built by new reef-building organisms adapted to the conditions of their time. On the biological front, the passage of 10 million years will have allowed for both extraordinary diversification and extinction. Species can evolve into entirely new forms within a fraction of this time, so the life forms of the future will be products of environments we can only guess at. Mammals, birds, reptiles, and fish may look as alien to us as the dinosaurs would have to the earliest mammals. Some of our familiar animals may have vanished entirely, replaced by descendants adapted to new climates and food sources. Life will persist, but it will do so in ways shaped by the unceasing pressures of natural selection. If intelligent life persists, it will have had the opportunity to evolve culturally and technologically in directions unimaginable to us. Over such spans, languages change beyond recognition. Political entities rise and fall, and technologies emerge that can reshape the destiny of entire species. It is possible that any future civilization will have mastered control over planetary systems, geoengineering their world to maintain habitability despite changes in the sun's brightness or the movement of continents. They may even manipulate the orbits of planets or moons to suit their needs, redirecting asteroids or comets as resources. The moon, now orbiting tens of thousands of kilometers farther from Earth than in our time, will continue its gradual retreat. Its gravitational influence on tides will be noticeably weaker, changing the daily ebb and flow of coastal waters. This shift will alter coastal ecosystems and may influence the migration patterns of marine species that rely on tidal cues. In the far future, these small changes accumulate into profound shifts in the structure of life itself. In the solar system beyond Earth, changes will also be evident. the surfaces of planets and moons will bear fresh scars from countless asteroid and comet impacts. Some worlds may have undergone dramatic geological transformations, volcanic eruptions on Io, methane rainfall reshaping the surface of Titan, or dust storms on Mars burying and revealing features over millions of years. Space probes launched by humans in the distant past might still exist, though battered by micrometeoroids and radiation. Some may have been captured by other celestial bodies, or even ejected entirely from the solar system, drifting into the interstellar void. Stellar evolution will be ongoing across the galaxy. Massive stars will live and die, leaving behind neutron stars and black holes. New star clusters will form, while others will disperse into the wider galactic population. Supernovae will periodically light up the sky, leaving behind clouds of heavy elements that will one day form planets, moons, and life. In 10 million years, the night sky will be a record of both creation and destruction, each bright point a chapter in a story that spans billions of years. The gravitational relationship between the Milky Way and Andromeda will have tightened noticeably, though their actual collision is still billions of years away. Andromeda will be visibly larger and brighter, a prominent and growing feature of the night sky. Its increased gravitational influence may subtly alter the orbits of stars at the fringes of both galaxies, setting the stage for the complex dance that will eventually merge them into a single giant elliptical galaxy. The Oort cloud, the vast halo of icy bodies surrounding the solar system, will still be in place, but passing stars and molecular clouds will have disturbed it countless times, sending waves of comets inward. Some will pass harmlessly by the planets, offering dazzling displays of tails stretching across the sky. Others may collide with planets or moons, delivering both destruction and raw materials. These impacts could reshape the geological and biological history of worlds throughout the solar system. For any beings who call Earth home 10 million years from now, the world will be profoundly different, yet still familiar in the most fundamental ways. The sun will still rise and set, the moon will still grace the night sky, and the stars will still glitter overhead. But the constellations will be new, the continents rearranged, the oceans reshaped, and the life forms unlike anything we see today. The deeper truth is that, over such spans of time, change is inevitable and unstoppable. Whether life thrives or declines, whether civilizations rise or vanish, the clock of the universe will continue to tick, marking each moment with slow, majestic transformations. 10 million years is not the end of anything. It is just another turn of the cosmic wheel, carrying the universe forward into its endless and ever-changing future. 100 million years ahead. 100 million years is an almost incomprehensible stretch of time when measured against human history. Civilizations, continents, climates, and even entire species come and go in mere fractions of this vast interval. While 1 million or even 10 million years may bring dramatic changes, 100 million years reshapes the Earth and the cosmos in ways that leave the present era almost unrecognizable. The slow, steady processes of geology and astronomy, which are barely noticeable over a human lifetime, have had time to produce grand, irreversible transformations. By this point, the face of our planet will be entirely different from anything we know today. The slow motion of plate tectonics will have rearranged the continents into a configuration that would be alien to our eyes. The Atlantic Ocean may have continued to widen to its maximum extent before eventually beginning to close again, pulling the Americas toward Europe and Africa. In the Pacific, vast changes will have taken place as island chains grow, merge, or vanish into the sea, and as subduction zones pull the ocean floor down into the mantle. Entire mountain ranges will have risen and eroded away in this span of time, leaving behind only ancient roots in the form of rolling hills or plateaus. The collision between Africa and Europe, which began millions of years earlier, will be long complete by now, forming a massive, Himalayan-scale mountain range where the Mediterranean Sea once existed. The remnants of that sea will have been swallowed by geological uplift, or reduced to a series of inland lakes. Other seas will have opened in different parts of the globe. Australia may have merged with Southeast Asia, altering ocean currents and reshaping regional climates. Antarctica's position will dictate whether it remains an icy wasteland or moves into a warmer latitude. potentially blooming with plant life again, as it once did during the age of dinosaurs. Climate will have shifted through multiple cycles over this immense period. Ice ages and warm periods will have alternated, each leaving its mark on the biosphere. If the sun continues its slow increase in brightness, something we know it will, global temperatures will be warmer overall than they are today. This warming will alter rainfall patterns, sea levels, and the distribution of ecosystems. Tropical belts may expand, deserts may grow, and polar regions may be less icy than in our time. Over tens of millions of years, these changes will completely redraw the map of life on Earth. Life itself will be almost entirely different from what we know now. 100 million years is more than enough time for evolution to replace almost every existing species with descendants better suited to the new conditions. Entirely new forms of life will have emerged to fill ecological niches, and some of today's dominant species will have left no living descendants at all. Whether mammals remain the dominant large animals or whether another group takes their place is unknowable. But history shows that dominant clades often give way to others when environments change. In the oceans, the movement of continents will have dramatically altered marine habitats. New shallow seas may host vibrant ecosystems, while other regions may be barren deep oceans with little life. Coral reefs, if they survive at all, will likely be formed by entirely new types of reef builders, as the species we know today will be long extinct. The deep ocean, insulated from rapid environmental shifts, will still host strange and diverse life forms, many of which will be evolutionary descendants of species alive in our time. The moon will by now be nearly 400,000 kilometers farther from Earth than it is today. Its gravitational pull will be weaker still, further diminishing tidal effects. Total solar eclipses will be rarer and shorter, with the moon's apparent size in the sky noticeably smaller. This may subtly alter biological rhythms in marine and coastal ecosystems, which have evolved to synchronize with tidal patterns. From an astronomical perspective, the sky will have changed beyond recognition. Over 100 million years, the Sun and its planetary system will have traveled a considerable distance around the Milky Way, perhaps completing almost half of a galactic orbit. The solar system's surroundings will be entirely new, different star fields, nebulae, and perhaps even closer encounters with passing stars. The constellations of this distant future will bear no resemblance to those of the past. They will be purely the product of the star positions in this epoch. In this time frame, the Andromeda Galaxy will be dramatically closer than it is today, though the actual merger with the Milky Way will still be far in the future. It will dominate a larger portion of the night sky, its spiral structure clearly visible even to the unaided eye in dark conditions. This slow approach will subtly alter the gravitational environment of both galaxies, possibly disturbing outer stars and dwarf galaxies. Supernovae will have occurred in abundance across the galaxy, enriching the interstellar medium with heavy elements. Some of these explosions will have been visible from Earth, temporarily outshining entire galaxies in the night sky. Others will have seeded star-forming regions with the materials necessary for new planetary systems and, potentially, new life. Within the solar system itself, the planets will still exist largely as they do today, though their surfaces and atmospheres will have evolved. Mars, still geologically inactive, will bear the scars of 100 million more years of meteor impacts. Jupiter's moon, Io, will continue to be reshaped by volcanic activity. Saturn's rings may have largely disappeared by this time, having either dissipated into space or fallen into the planet itself. Moons such as Europa or Enceladus may have experienced changes in their subsurface oceans due to shifts in gravitational heating from their parent planets. If humanity, or any intelligent descendants, still exist, their technological and cultural evolution over 100 million years will be beyond anything we can now imagine. Civilizations may have risen and fallen countless times, each leaving behind traces for future archaeologists to uncover. Advanced societies could manipulate entire star systems, move planets, or harness the energy of stars directly. Alternatively, intelligent life could have vanished from the solar system entirely, leaving only silent monuments and scattered probes drifting in space. Even if life survives, it will be shaped by deep time. The biosphere will have endured asteroid impacts, volcanic supereruptions, climate shifts, and possibly even encounters with interstellar clouds or nearby supernovae. Each of these events will have been both a crisis and an opportunity, wiping out some species while opening the door for others to flourish. Evolution is relentless, and 100 million years ensures that the winners of today's struggle for survival will be unrecognizable in the far future. In the grand tapestry of the cosmos, 100 million years is still early in the universe's lifespan. Stars will still burn brightly in the night, galaxies will still be forming, and the expansion of the universe will still be in its accelerated phase. The universe will remain an active, dynamic place, full of creation and destruction, even as the slow ticking of cosmic time carries it toward much more distant horizons. The geological record 100 million years from now will be a layered archive of events long forgotten by the present. Layers of sediment will tell the story of shifting climates, mass extinctions, and recoveries. Fossils from this future era will be utterly alien to us. Creatures shaped by ecosystems we cannot picture, living in climates and continents we have never known. Perhaps some familiar lineages will persist, much as crocodiles and certain sharks have survived for hundreds of millions of years. But even they will have evolved in ways that make them distinct from their ancestors. Erosion will have erased almost every trace of our current age from the surface. Cities will have long since crumbled and been buried. The tallest skyscrapers of today will be nothing more than mineralized debris, their outlines discernible only to geologists who dig deep enough to find them. Radioactive isotopes, plastics transformed by geological pressure, and rare alloys may be among the only surviving clues that an advanced technological civilization once flourished here. Even those markers will eventually be altered beyond recognition by the planet's dynamic systems. Over such an immense span, the planet's atmosphere itself may have changed in its composition. The steady brightening of the sun will have increased the rate of evaporation, altering the water cycle and possibly leading to reduced ocean volume if evaporation outpaces replenishment from geological processes. On land, ecosystems will have shifted to reflect new patterns of rainfall and temperature. Plants will have adapted to higher light levels and warmer conditions, and entirely new forms of vegetation may dominate the landscape. The moon, continuing its slow retreat, will now be a visibly smaller companion in the night sky. Its gravitational influence, though still present, will no longer be the dominant force behind tides. Coastal habitats dependent on strong tidal flows will have transformed or vanished entirely. The lunar surface itself will bear millions of new craters from meteorite impacts, silent evidence of the unceasing bombardment that all airless worlds endure. The solar system will have traveled a vast distance around the Milky Way during this time, bringing it into entirely new stellar neighborhoods. We may have passed through denser star fields, giving the night sky more points of light than today, or perhaps through more isolated regions where the stars seem sparse and distant. Each new neighborhood brings with it the possibility of gravitational encounters, close approaches with other stars that may disturb distant comets and send them plunging toward the inner planets. Supernovae, some potentially within a few hundred light years, will have illuminated the sky at various points in this 100 million year journey. The closest of these could have left a measurable impact on Earth's climate and biosphere, perhaps even triggering extinctions. But they would also have enriched the interstellar medium with heavy elements, seeding future planetary systems with the ingredients for life. If intelligent life, whether human or otherwise, persists into this era, their technology may be as different from ours as ours is from the stone tools of the Paleolithic. They might manipulate planetary climates at will, move stars to new positions, or travel between galaxies as easily as we send probes to the moon today. Their understanding of physics may allow them to harness phenomena we cannot even name, bending space and time in ways that defy our current imagination. Alternatively, they may have transcended physical form altogether, existing as patterns of energy or information, woven into the very fabric of the cosmos. It is equally possible that intelligent life will be absent entirely, having succumbed to cosmic hazards, self-inflicted disaster, or the sheer unpredictabilities of evolutionary paths. If so, the Earth will be left to its own devices, its surface reclaimed entirely by nature, its past civilizations forgotten except for whatever fragments endure in the geological record. In such a scenario, future intelligent beings, if they evolve, might one day discover those traces and wonder about the beings who came before them. On the galactic stage, the Milky Way will still be vibrant and full of star-forming regions. Massive stars will continue to live brief, brilliant lives before dying in spectacular explosions. Star clusters will form and disperse, and the slow dance with Andromeda will continue to tighten the gravitational bond between the two galaxies. The approach will be slow but inevitable, setting the stage for an eventual merger that will forever change the shape of our galactic home. From the perspective of the universe as a whole, 100 million years is still the age of light and abundance. The stars will continue to shine, galaxies will continue to collide and merge, and black holes will continue to grow. The deep, cold future in which the universe grows dark is still far away. For now, the cosmos remains alive with energy, movement, and creation. 100 million years ahead, Earth will not be the same world we know, but it will still be a dynamic, living planet orbiting a star that is slowly growing brighter. Its continents will have shifted, its climates will have transformed, and its life forms will be almost entirely new. The sky above will hold unfamiliar stars, nebulae, and perhaps the faint arc of Andromeda looming ever larger. Whether there are eyes to see it or not, the universe will continue its slow, majestic evolution, carrying everything forward into the ever-unfolding tapestry of cosmic time. 500 million years in the future, 500 million years from now, the universe will still be young compared to its ultimate fate, but Earth will be deep into a transformative stage that will permanently alter its surface, its oceans, its biosphere, and possibly its very capacity to support complex life. While earlier milestones such as 1 million or 100 million years bring dramatic change, the 500 million year mark introduces consequences of an entirely different order. Changes driven not just by tectonic drift or evolutionary shifts, but by the sun's inexorable brightening as it ages. The sun, like all main sequence stars, gradually increases in luminosity as it fuses hydrogen into helium in its core. Over 500 million years, its brightness will have risen by roughly 5 to 6% compared to today. That change, though seemingly modest, will trigger a cascade of climatic effects. Higher solar output means higher average global temperatures. While life is resilient, the biosphere's tolerance for such shifts has limits. This increase in heat will disrupt the delicate balance of Earth's climate systems, pushing them toward states that no longer resemble the patterns familiar to us. One of the most significant outcomes of this warming will be the acceleration of the carbonate-silicate cycle, a natural process that regulates atmospheric carbon dioxide over geological timescales. As temperatures rise, weathering of silicate rocks on continents will intensify, pulling carbon dioxide out of the atmosphere faster than volcanic activity can replenish it. This will cause a steady decline in CO2 levels, eventually reaching concentrations so low that most plants dependent on photosynthesis will struggle to survive. In fact, scientists estimate that by around 500 million years from now, the majority of C3 plants, the most common type on Earth today, including trees and staple crops, will be unable to carry out photosynthesis effectively. Only certain C4 plants, which can photosynthesize efficiently at lower CO2 levels, will endure, and even they will face eventual decline. This gradual collapse of plant life will reverberate through the entire food chain. Herbivores will die off, followed by the carnivores that depend on them. Complex ecosystems will fragment and vanish. The oceans will also feel the impact. As temperatures rise, evaporation will accelerate, leading to a slow but relentless loss of ocean water to space. Water vapor in the upper atmosphere will be broken apart by solar ultraviolet radiation, and the liberated hydrogen will escape into space. Over hundreds of millions of years, this process will gradually dry the planet. While at the 500 million year mark, the oceans will still exist, their volumes will be reduced, coastlines redrawn, and shallow seas may have evaporated entirely. Geologically, the face of the Earth will be as unrecognizable as it has been in every earlier epoch. The continents will have continued their slow, restless migration. Depending on the dynamics of plate movement, the landmasses may have merged into another supercontinent, a recurring pattern in Earth's history. with supercontinents such as Rodinia, Pangaea, and Gondwana appearing and breaking apart over hundreds of millions of years. If a new supercontinent exists at this time, it will dominate one hemisphere, with vast oceans stretching across the other. A supercontinent would have profound effects on climate. The interior regions, far from the moderating influence of the ocean, would likely be arid and subject to extreme temperature swings between day and night. Coastal regions might remain more habitable, but the overall diversity of climates would be reduced. Monsoons and seasonal storms could be more intense due to the way large land masses interact with atmospheric circulation patterns. Life, if still present in complex forms, will have had to adapt dramatically to these conditions. The dominant life forms of 500 million years from now might be hardy, heat-tolerant organisms capable of surviving in fluctuating or extreme environments. Coastal ecosystems could still harbor diversity, but vast areas of the land might be barren or sparsely populated by specialized forms of life. In the oceans, life may retreat to deeper, cooler waters, where conditions remain more stable. The moon will have continued its retreat from Earth, now perhaps some 20,000 kilometers farther than today. Tidal forces will be weaker still, subtly influencing ocean circulation patterns. The reduced tidal mixing could limit the distribution of nutrients in the oceans, further straining marine ecosystems already stressed by warming temperatures and reduced oxygen levels. From the perspective of the night sky, 500 million years brings changes on a galactic scale. The solar system will have traveled a significant fraction of its orbit around the Milky Way, passing through entirely new regions of the galaxy. Star fields will be unrecognizable, nebulae and star clusters completely different from those seen today. Some close encounters with other stars may have disturbed the outer reaches of the solar system, sending comets inward or ejecting icy bodies into interstellar space. The Andromeda Galaxy will loom even larger in the sky, perhaps spanning several degrees, its spiral arms distinctly visible. Though the final collision between Andromeda and the Milky Way is still billions of years away, gravitational interactions will already be subtly affecting the motions of stars in both galaxies. Dwarf galaxies that orbit the Milky Way may have been consumed, their stars adding to the growing halo of our galaxy. Supernovae will have continued to erupt across the sky, each one briefly outshining entire galaxies before fading into beautiful remnants of glowing gas and dust. Some of these explosions may occur close enough to Earth to influence its climate, though the exact impact would depend on the distance and energy of the event. Gamma-ray bursts, though rare, could also pose a threat, potentially stripping away parts of the atmosphere if one were to occur within a few thousand light years. If intelligent life survives into this era, it will have mastered technologies far beyond our comprehension. Such beings might live in artificial habitats orbiting the sun or drifting between stars. They may have engineered the Earth itself, managing its atmosphere and biosphere to counteract the sun's warming, or even move the planet to a more distant orbit to preserve habitability. Stellar engineering, redirecting mass within the sun to slow its evolution, might be within their capabilities. Alternatively, life may have left Earth entirely, migrating to more stable environments elsewhere in the solar system or in other star systems. Mars, icy moons like Europa, or artificial habitats could serve as refuges for descendants of life that began on Earth. If this is the case, Earth might be a world in decline, still beautiful, but increasingly hostile to the life forms that once flourished here. The half-billion-year mark is a turning point. While the planet remains active, the sun's growing luminosity is starting to tip the balance against complex life. The conditions that have allowed such life to thrive for hundreds of millions of years are beginning to unravel. The story of Earth is far from over, but it is entering a new and more precarious chapter. The transformation of Earth's biosphere at this stage will be profound. The familiar forests, grasslands, and oceans of our age will be reduced to ecosystems that are far more specialized and constrained by the limits of heat, light, and nutrient availability. Deserts may cover much of the land, dotted with hardy plants capable of surviving in poor soils and arid conditions. In regions where water still flows, it will likely do so seasonally, with flash floods and short-lived rivers feeding into shrinking inland seas. In the oceans, marine life will be increasingly concentrated in areas where upwelling brings nutrients from the deep to the surface. These regions, often near continental margins, will serve as oases for marine ecosystems. The open ocean, by contrast, may become increasingly barren, with reduced primary productivity as phytoplankton populations decline due to low nutrient availability and increased stratification of the water column. Volcanic activity will continue to play a role in shaping the landscape and the atmosphere. Over 500 million years, numerous super eruptions will have occurred, temporarily altering the climate and depositing vast layers of ash and lava. These events may provide brief boosts to atmospheric CO2, offering temporary relief to photosynthetic life in decline. Yet, in the long run, the geological carbon cycle will continue drawing down carbon dioxide, keeping the trend toward reduced plant life firmly in place. If a supercontinent exists during this era, the planet's interior dynamics will be significantly affected. Large landmasses insulate the mantle beneath them, potentially leading to the buildup of heat and the formation of massive volcanic provinces. Such events could reshape climate on a global scale, introducing bursts of warmth or cold depending on the interplay of volcanic emissions and solar output. Coastal areas of the supercontinent could experience monsoon-like patterns of intense seasonal rainfall, while interior deserts remain parched and inhospitable. The evolution of life in these conditions will likely favor adaptability and resilience. Organisms capable of withstanding extreme heat, irregular access to water, and low nutrient levels will dominate. These could range from heat-tolerant reptiles and burrowing mammals to entirely new lineages of life with physiological systems fine-tuned for efficiency. In the oceans, life may cluster around hydrothermal vents, where geothermal energy provides an alternative to sunlight as a source of energy for ecosystems. The gradual loss of ocean water to space will be an ongoing background process. While the change over a few million years is minimal, over 500 million years, the cumulative effect is substantial. Shallow seas could dry out completely, leaving behind salt flats and mineral deposits. Former continental shelves may be exposed, becoming part of the terrestrial landscape. This reduction in ocean coverage will further amplify climate extremes, as large bodies of water act as stabilizers of temperature and weather patterns. The moon, now farther from Earth than ever before, will be smaller in the sky, and total solar eclipses may have become rare spectacles, lasting only moments. Its tidal influence will be weak enough that coastal tidal zones may no longer experience the dramatic changes in water level that characterize our present-day shores. This could lead to the disappearance of many tide-dependent species, from small crustaceans to larger predators that rely on these ecosystems for food. From the perspective of the night sky, 500 million years will completely rewrite the stellar backdrop. The solar system will have passed through multiple regions of the Milky Way, each with its own distribution of stars, nebulae, and interstellar clouds. Encounters with such clouds could temporarily dim sunlight by scattering and absorbing some of its energy, potentially causing brief cooling periods on Earth. Andromeda will dominate a significant section of the night sky by now, appearing as a vast glowing arc, its spiral arms easily distinguishable without telescopes. Its gravitational influence on the Milky Way will be stronger than ever, subtly perturbing the orbits of stars in the outer halo. These shifts could indirectly affect the solar system if distant gravitational nudges ripple through the Oort cloud, sending a fresh wave of comets toward the inner planets. Supernovae in our galactic neighborhood will still occur, each one enriching the interstellar medium with heavier elements. Depending on their proximity, they could affect life on Earth either through radiation exposure or atmospheric changes. Yet these events also serve as part of the ongoing cosmic recycling process, ensuring that new generations of stars and planets continue to form from the ashes of their predecessors. If advanced life remains active in the solar system at this time, it may have implemented large-scale planetary engineering to counteract the sun's warming. Possible strategies could include deploying massive orbital shades to reduce solar radiation, altering the atmosphere to retain higher CO2 levels for photosynthesis, or even slowly moving Earth to a wider orbit through gravitational assists from asteroids or other planets. These feats, while inconceivable to us today, would be within the realm of possibility for a civilization with hundreds of millions of years of technological advancement. Alternatively, the solar system might be largely devoid of complex life, with Earth entering a phase where only extremophiles, organisms adapted to the harshest conditions, remain. In such a case, the legacy of earlier life could be preserved in the geological record, in dormant spores hidden deep underground, or in frozen relics in the outer solar system. The half-billion-year milestone represents the early stages of Earth's long farewell to complex life. The sun's increasing brightness, the decline of atmospheric carbon dioxide, and the gradual drying of the planet set the stage for a slow but inexorable shift toward a less hospitable world. Yet, even as the biosphere struggles, the planet remains dynamic, and the universe around it is still a vibrant, active place. The stars will continue to shine, galaxies will continue to form and evolve, and cosmic events both beautiful and destructive will continue to shape the grand narrative of existence. 500 million years from now, whether seen by the eyes of intelligent beings or only by the silent witness of geology, Earth will be a place of extremes, familiar in its outlines but alien in its details. It will stand as a testament to both the resilience and the fragility of life in the face of deep time. 1 billion years from now, 1 billion years into the future, Earth will be a profoundly different world. While the planet will still orbit the sun, and the moon will still circle Earth, the conditions that once made our home a cradle for complex life will have changed in ways that are both subtle and catastrophic. The slow, steady processes that began in earlier epochs, solar brightening, continental drift, atmospheric change, and biological evolution, will have pushed the biosphere toward a tipping point. By this time, the sun will be roughly 10% more luminous than it is today. That increase, while gradual over geological timescales, is devastating for a world like ours. Global temperatures will be significantly higher than in the present day. The extra heat will intensify the rate of evaporation from the oceans, pumping more water vapor, a powerful greenhouse gas, into the atmosphere. This, in turn, will accelerate warming in a dangerous feedback loop. The loss of water to space, already underway for hundreds of millions of years, will have reached a critical point. As water vapor in the upper atmosphere is broken apart by ultraviolet light from the sun, hydrogen escapes into space, never to return. Over 1 billion years, this process will have stripped away a significant fraction of Earth's oceans. Vast areas that were once covered by water will be exposed as dry, cracked basins, their surfaces coated in salt and mineral deposits. The reduced ocean volume will drastically alter weather patterns. Without the moderating influence of large bodies of water, temperature extremes will be more severe, scorching heat during the day in many regions, and cold nights in others. Coastal climates, once mild and stable, will become volatile, with seasonal storms that are more intense and destructive than anything in the human historical record. Atmospheric composition will have shifted dramatically. Carbon dioxide levels will have dropped to levels too low to support most forms of photosynthesis, leading to the near-total collapse of plant life hundreds of millions of years earlier. In place of today's lush forests and grasslands, Earth's land surfaces will be dominated by deserts, barren rock, and the remnants of heat-adapted organisms clinging to existence in sheltered niches. The biosphere will be dominated by microbes and extremophiles, organisms capable of surviving in high heat, intense radiation, and low-nutrient environments. Any surviving complex life will be confined to extreme environments. Deep ocean trenches, where cooler temperatures persist, may harbor isolated pockets of more diverse ecosystems. Underground habitats, shielded from the sun's heat and radiation, could also serve as refuges. On the surface, life might endure in polar regions, where temperatures are relatively lower, though even these areas will be far warmer than they are today. Geologically, the continents will have shifted once again. 1 billion years is more than enough time for a complete rearrangement of the planet's surface. Another supercontinent may have formed and broken apart again during this period. Continents will have collided, raising mountain ranges that in turn eroded back into plains. Ocean basins will have opened and closed, and volcanic activity will have reshaped coastlines and islands countless times. The moon will now be tens of thousands of kilometers farther from Earth than it is today. continuing its slow drift outward. Its apparent size in the sky will be smaller, and total solar eclipses may no longer be possible at all. Tides will be weaker than ever, and in many places the tidal rhythm will be barely noticeable, a far cry from the dynamic tidal zones that once fueled rich coastal ecosystems. From the perspective of the night sky, 1 billion years brings changes that are staggering to imagine. The sun, still in its stable main sequence phase, will shine more brightly, but the constellations will bear no resemblance to those of the present day. The solar system will have completed nearly 5 full orbits around the Milky Way's center, each orbit taking roughly 225 million years. During that journey, we will have passed through countless different stellar neighborhoods, regions dense with stars, regions nearly empty, and perhaps even through interstellar clouds capable of dimming the sun's light for thousands of years. By this point, the Andromeda Galaxy will be close enough that its spiral arms will dominate a large portion of the night sky. The gravitational interaction between our galaxies will be unmistakable, with streams of stars stretching between them. The two galaxies will be well on their way toward a collision, which will occur a few billion years later. Supernovae will have come and gone, as they always do. Some may have erupted close enough to Earth to impact the biosphere, perhaps causing temporary cooling or even mass extinctions among the few life forms remaining. Others will have been distant spectacles, brief points of brilliance in the night sky that fade into haunting nebulae over thousands of years. If intelligent life still exists, whether descended from humanity or evolved independently, it will have had to adapt in extraordinary ways. Surface habitation on Earth may be impossible for large populations, driving advanced civilizations underground, underwater, or entirely off-planet. They might live in artificial habitats orbiting the sun, or on other planets and moons in the solar system. It is also possible that they will have migrated to other star systems entirely, abandoning Earth as it becomes increasingly hostile. Technological mastery at this stage could include planetary-scale climate control, the ability to adjust Earth's orbit, or even engineering the sun's output to slow its increase in luminosity. Vast orbital structures could shield the planet from excess sunlight. Alternatively, life might have chosen to disperse, inhabiting countless artificial worlds scattered throughout the galaxy, no longer tied to a single planet. If no intelligent life remains, Earth will simply be a warm, mostly dry world, dotted with microbial life and perhaps a few hardy multicellular survivors. The rich, complex ecosystems of the past will be gone, their memory preserved only in the fossil record. Without life to replenish oxygen, the atmosphere may begin to lose its current composition, shifting toward a state more like that of early Earth, long before animals evolved. In cosmic terms, 1 billion years is still an age of light. The universe will continue to teem with galaxies, stars, and planets. The accelerating expansion of space will have carried the most distant galaxies farther away, but the nearby universe will remain richly populated with luminous matter. Star formation will still be active in many regions, and the cycle of birth and death among stars will continue. 1 billion years from now, Earth will still exist, but it will be a shadow of the world we know today. Whether seen through the eyes of its last inhabitants, through the lens of distant observers, or left to spin silently through space, it will stand as both a monument to life's resilience and a warning of its fragility. The forces shaping it will be the same as they have always been: gravity, radiation, chemistry, and time, relentlessly working to transform it into something new. The ecosystems that survive at this stage will be a far cry from the lush and interconnected web of life that defined much of Earth's history. In place of vast forests and vibrant coral reefs, we will see hardy microbial mats coating rocks in the few regions where moisture lingers. These could be in deep valleys, polar areas, or the shaded interiors of craters where temperatures are cooler. On land, any remaining complex plants will be relic species, adapted to extremely low carbon dioxide levels and capable of conserving water with astonishing efficiency. The oceans, though reduced in volume, will still hold life, primarily microscopic organisms able to survive in warmer, saltier, and less oxygen-rich waters. Around hydrothermal vents on the seafloor, communities of extremophiles will continue to thrive, drawing energy from the planet's internal heat rather than the diminishing bounty of photosynthesis at the surface. These vent ecosystems will be among the last strongholds of biodiversity, isolated from the harsh conditions above. Over the billion years preceding this point, countless geological cycles will have reshaped the continents and ocean basins. Mountain ranges will have risen and eroded away more than once. Subduction zones will have recycled vast swaths of the crust into the mantle. New island chains will have emerged from volcanic activity, only to sink beneath the waves. The very face of the planet will bear no resemblance to the maps we know today. If a supercontinent has formed in this era, it will have its own distinct climate challenges. Interiors of such vast landmasses will be inhospitable deserts, while coastlines may be prone to violent storms due to the contrast between hot land and relatively cooler oceans. Glacial cycles, if any remain, will be muted or absent due to the overall warmth of the planet. Weathering rates on exposed rock will be high, driving the continued drawdown of the carbon dioxide and sealing the fate of photosynthetic life. From the perspective of any intelligent beings alive in this era, the night sky will be awe-inspiring, but utterly alien. The constellations will be long forgotten, replaced by entirely new stellar arrangements. The Andromeda Galaxy will dominate the sky with breathtaking clarity, its spiral arms stretched and distorted by the gravitational interplay with the Milky Way. Streams of stars torn from both galaxies will form glowing arcs visible to the naked eye. These changes will be a prelude to the eventual galactic merger, which, though still billions of years away, will already be reshaping the heavens. Stellar encounters will continue to subtly affect the solar system. Passing stars could disturb the orbits of comets in the Oort cloud, sending them inward toward the inner planets. Some might strike Earth, producing massive craters on its now largely barren surface. While such impacts would have been catastrophic for a world teeming with life, in this late stage they would have little effect beyond temporarily altering local conditions. Supernovae will still erupt in the galaxy, but fewer massive stars will be born compared to earlier cosmic history. The galaxy will be older, with a greater proportion of long-lived, dimmer stars. Yet the drama of stellar death will remain a fixture of the night sky, providing moments of brilliance against the backdrop of an increasingly settled cosmos. If advanced civilizations survive into this epoch, their technological capabilities will likely be beyond the comprehension of earlier humans. They may have abandoned planetary surfaces altogether, living in orbiting habitats or even in engineered environments within stars themselves. The manipulation of gravity, space-time, and stellar processes could be routine. For such beings, the warming of Earth would not be a crisis, but an opportunity, perhaps to reshape the planet into something entirely new, or to preserve it as a living museum of its earlier eras. Alternatively, Earth may be entirely devoid of intelligence. If this is the case, it will quietly continue its transformations, with the remaining life evolving slowly in isolated refuges. These survivors will be direct descendants of microbes that predate humanity by billions of years, making them some of the most enduring forms of life ever to exist on the planet. Geologically, volcanic activity will still shape the surface, though at a slower rate as the planet gradually cools internally. Earthquakes, mountain-building events, and eruptions will still occur, but the overall vigor of plate tectonics may be reduced compared to earlier times. The gradual cooling of the core will also affect the planet's magnetic field, potentially weakening it. A weaker magnetic field would allow more solar and cosmic radiation to reach the surface, further stressing any remaining life. In the grander cosmic picture, 1 billion years is still an age of brilliance. The universe will not yet be old enough for most stars to have burned out, and galaxies will still be rich with luminous matter. Star formation will continue, though at a lower rate than in the universe's peak years. The cosmic web of galaxies will still be visible in deep space, even as the most distant ones slip beyond the observable horizon due to the accelerating expansion of the universe. On Earth, however, the story will be one of decline from the perspective of complex life. The rich dynamic biosphere that characterized much of the planet's past will be gone, replaced by a far simpler and more austere version. The conditions that allowed for the flourishing of plants, animals, and human civilization will be a distant memory. Yet in its persistence, whether through microbes in deep rock, extremophiles in hydrothermal vents, or organisms clinging to the cold edges of polar regions, life will still demonstrate its remarkable ability to endure. 1 billion years from now, the sun will still shine, the earth will still spin, and the moon will still orbit. The familiar cycles of day and night, phases of the moon, and seasons, though altered, will continue. But the surface of the planet will be a place of heat, dryness, and scarcity, a world shaped by forces both familiar and strange. Whether witnessed by intelligent eyes, recorded by machines, or left to unfold in complete solitude, this chapter of Earth's history will stand as a testament to the inevitability of change in the universe. 5 billion years ahead. 5 billion years from now, the Sun will be entering the final stages of its life as a main sequence star. The long, stable era that began over 9 billion years earlier, an age in which the Sun's steady light made Earth a cradle for life, will be drawing to a close. What happens in this epoch will be nothing less than a transformation of the solar system itself. By this time, the Sun will have exhausted the majority of the hydrogen fuel in its core. Without hydrogen fusion to counteract the inward pull of gravity, the core will contract, heating up until fusion ignites in a surrounding shell of hydrogen. This change will cause the Sun's outer layers to expand dramatically, beginning its transition into a red giant. As the Sun swells, its luminosity will increase hundreds of times beyond its current brightness. The outer layers will stretch outward, engulfing the orbits of Mercury and Venus. Whether Earth will be swallowed is still debated. Models suggest that while the Sun's outer atmosphere will extend nearly to Earth's current orbit, tidal forces and drag from the Sun's expanding atmosphere might cause our planet to spiral inward and be consumed. Even if Earth survives physically, the conditions will be utterly inhospitable. Before this final engulfment, the increasing heat will transform Earth into a world unlike anything in its past. Oceans will have been gone for billions of years. The surface will be a scorched wasteland, its rocks baked and fractured by relentless solar radiation. Any remaining atmosphere will be thin and dominated by heavier gases. As lighter molecules escape into space, temperatures will soar to hundreds of degrees Celsius, rendering the surface molten in some regions. The moon will still exist if it has not been destroyed by earlier tidal interactions or impacts, but its orbit will be altered by the shifting gravitational dynamics of the expanding Sun-Earth system. If Earth is engulfed, the moon will vanish with it, pulled into the Sun's outer layers. If Earth survives, the moon will orbit a planet transformed into a barren, airless rock, its tidal role long since irrelevant. Farther out in the solar system, the changes will be less catastrophic but still dramatic. The ice giants Uranus and Neptune, and possibly even the Kuiper Belt, will receive far more heat than they do today, altering their atmospheres and potentially triggering new weather systems. Moons with icy surfaces, like Europa, Enceladus, and Triton, may briefly become warm enough to melt, creating temporary oceans before evaporating into space. In these outer reaches, conditions might become suitable for life, at least for a short period, as the warmth from the swollen sun reaches them. The asteroid belt will be destabilized by the changing gravitational balance, sending some objects tumbling into the inner solar system. However, with no oceans or biosphere left on Earth, these impacts will be of geological interest only, not biological consequence. In the broader sky, the view will be completely unlike anything seen in earlier eras. The Andromeda Galaxy will no longer be a distant companion. It will have merged with the Milky Way billions of years earlier, forming a single giant elliptical galaxy often referred to as Milkomeda. The collision will have radically altered the night sky. The ordered spiral arms of the Milky Way will be gone, replaced by a smooth, hazy glow filled with countless merged star systems. Streams of stars thrown into intergalactic space during the collision will streak faintly across the darkness. The Sun's transformation into a red giant will be one of the most spectacular sights for any observers in the solar system or nearby star systems. Its swollen, ruddy disk will dominate the sky, many times larger than the Sun appears today. The light it casts will be dimmer per unit area, but spread across a vastly larger surface, bathing the solar system in an eerie, copper-colored glow. If advanced civilizations exist in this era, they will face existential decisions. For life tied to Earth, survival will require relocation, either to the outer planets, to engineered habitats, or to other star systems entirely. Technologies might exist to move entire planets outward, using gravitational assists from asteroids or passing stars, or by directing powerful propulsion systems at the planetary core. Alternatively, civilizations may choose to abandon the solar system altogether, seeking refuge around younger stars with stable habitable zones. The Sun's red giant phase will not last forever. After expanding to its maximum size and shedding much of its outer mass into space, the Sun will contract into a white dwarf, a dense Earth-sized remnant composed primarily of carbon and oxygen. This stellar corpse will no longer produce energy through fusion, but will radiate away its residual heat for billions of years. The planetary nebula created by the Sun's ejected outer layers will glow briefly in the sky, a delicate shell of gas expanding into the interstellar medium before fading into darkness. Earth's fate in this final act will depend on whether it survives the Sun's expansion. If it is engulfed, it will vaporize within minutes, its matter becoming part of the Sun's atmosphere. If it survives, it will orbit a cold, dead star, its surface frozen and lifeless under a darkened sky. Either way, the age of Earth as a cradle for life will have ended long before. The outer planets may continue to orbit the white dwarf, their icy surfaces preserved in deep cold. Any remaining moons or dwarf planets might remain geologically active for a time due to tidal heating, but without sunlight, they will eventually become frozen relics. The Kuiper Belt and Oort cloud will persist for some time, their icy bodies slowly eroded by cosmic rays and distant stellar encounters. 5 billion years ahead, the solar system will be a very different place, quieter, emptier, and colder, despite the fiery drama of the red giant phase. The dynamic interplay of planets, moons, and the Sun will have given way to a simpler system dominated by a faint stellar ember, and the remnants of worlds that once teemed with activity. In cosmic terms, this moment marks the end of a chapter, but not the end of the story. The white dwarf Sun will continue to orbit within Milkomeda, a small remnant in a galaxy filled with other stars at various stages of life. Over trillions of years, it will cool, fade, and eventually become a black dwarf, a dark, cold sphere invisible against the backdrop of space. But in the 5 billion year future, the universe will still be vibrant in many places. Even as the solar system enters its twilight, the transformation of the Sun into a red giant will not be a single, smooth event, but a complex and turbulent process. As the hydrogen-burning shell around the inert helium core grows hotter, the outer layers of the Sun will swell and contract in pulses. Each pulse will cause fluctuations in luminosity and size, altering the amount of radiation reaching the planets. The Sun's outer atmosphere will become unstable, with massive streams of gas escaping into space, forming a slow but steady stellar wind far denser than anything the solar system experiences today. This enhanced solar wind will strip away what little atmosphere remains around Earth, Mars, and possibly some of the larger moons. The increased radiation will sterilize any exposed surfaces, making survival impossible for any remaining biological material not deeply buried underground or encased in protective structures. Over millions of years, this stellar wind will carry away a substantial fraction of the Sun's mass, weakening its gravitational hold on the planets and causing their orbits to drift outward. The orbital expansion might, in theory, save Earth from being directly engulfed, but the intense heat would still render it uninhabitable long before. Any surviving technology or infrastructure left on the surface would be destroyed by thermal stress, radiation, and the constant bombardment of high-energy particles. For the outer solar system, this will be a moment of opportunity. Moons and planets that were once icy wastelands could thaw under the increased warmth, creating temporary seas and atmospheres. Europa's buried ocean might breach its icy crust. Titan's methane lakes could evaporate into thick, hazy skies, and Pluto's surface could briefly transform from frozen nitrogen plains to a more active environment. These changes, however, will be short-lived in cosmic terms, lasting only a few 100 million years at most, before the Sun sheds too much mass and dims into its white dwarf phase. The spectacle of the Sun's red giant phase will be unparalleled. From a surviving world in the outer solar system, the Sun will appear as a massive, swollen sphere dominating the sky, casting a dim reddish light over landscapes that had once been cloaked in deep cold. For any intelligent observers, whether human descendants or alien visitors, this will be both a scene of beauty and a reminder of the inevitable impermanence of stellar systems. As the Sun approaches the end of its red giant life, it will enter the helium flash stage. When the contracting helium core reaches sufficient temperatures, helium fusion will ignite explosively in a matter of minutes, though the energy will be absorbed by the Sun's outer layers rather than released as a cataclysm visible from afar. This ignition will stabilize the Sun temporarily, shrinking it slightly while it burns helium into carbon and oxygen. But this stability will last only a few 100 million years, a brief reprieve before the Sun once again swells and sheds its outer layers for the final time. The shedding of these layers will produce a planetary nebula, a vast glowing shell of gas expanding into space. For a few tens of thousands of years, this nebula will shine brightly, illuminated by ultraviolet light from the newly exposed white dwarf at its center. The nebula's colors will depend on the elements present: greens from ionized oxygen, reds from hydrogen, blues from helium. From within the solar system, it would be a breathtaking curtain of light wrapping around the dying star. From interstellar space, it would be a jewel-like bubble floating in the darkness, a cosmic announcement of the Sun's death as a main sequence star. The white dwarf that remains will be a stark contrast to the Sun we know. Roughly the size of Earth, but containing half the Sun's original mass, it will be an object of incredible density. A teaspoon of its material would weigh billions of tons. It will no longer produce energy through fusion, but will instead slowly cool over billions of years, radiating away its stored heat. In the gravitational reshuffling that follows the Sun's mass loss, the orbits of the remaining planets will expand significantly. Some may become unstable, with close encounters leading to ejections from the solar system entirely. The asteroid belt, Kuiper belt, and Oort cloud will be disrupted, sending waves of debris both inward toward the white dwarf and outward into interstellar space. If advanced civilizations survive this transition, their fate will depend on preparation. They might inhabit vast orbital habitats powered by fusion, or by harvesting energy from the white dwarf's residual heat. They might migrate to other star systems well before the red giant phase begins, leaving automated stations behind to monitor the death of the Sun. In some scenarios, civilizations might even attempt to capture passing stars, guiding them into orbit around the white dwarf to create new sources of light and heat. For any remaining life in the outer solar system, the red giant phase will be a fleeting window of warmth and habitability. Microbial life buried in the ice of moons like Enceladus or Ganymede might briefly awaken, replicate, and evolve before the environment freezes again. The red giant Sun could briefly transform these frozen worlds into liquid water havens, echoing the habitable conditions Earth once enjoyed billions of years earlier. Once the Sun becomes a white dwarf, however, the era of warmth will end forever. The outer planets and moons will return to deep freeze, and the solar system will settle into a long, slow fade toward darkness. The planetary nebula will disperse into the galaxy, contributing its elements to the next generation of stars and planets. The white dwarf will shine faintly for billions of years before cooling into a black dwarf, an object so cold and dark it is invisible to all but the most sensitive instruments. 5 billion years ahead marks the end of the solar system as a vibrant, sunlit environment. Whether observed by the descendants of humanity, alien travelers, or simply the indifferent cosmos, this transformation will be a final, irreversible shift. The bright yellow sun of our time will be gone, replaced by the ghostly ember of a once mighty star, drifting silently in the vastness of space. And yet, in this ending, there is continuity. The elements forged in the sun's core and scattered into space will become part of other worlds, other stars, and perhaps other forms of life. The story of the sun and its planets will not end. It will simply change chapters, becoming part of the ongoing cosmic cycle that has been at work since the dawn of the universe. 10 billion years into the future. By the 10 billion year mark, the solar system as we know it will be long gone. The sun will no longer shine as the bright yellow star that sustained life on Earth. It will be a small, dense, cooling remnant, a white dwarf, slowly fading into the darkness of space. Its planetary system, once teeming with activity, will have transformed into a sparse collection of surviving planets, moons, asteroids, and comets drifting in wide orbits under a much weaker gravitational grip. The white dwarf sun will be roughly the size of Earth, but still contain about half of its original mass. Its surface temperature will remain high compared to most objects in the galaxy, tens of thousands of degrees Kelvin when freshly formed. But after 5 billion years in this state, it will have cooled significantly. Its glow will be faint, casting only a dim light on any remaining worlds. The habitable zone, once spanning a comfortable distance that allowed liquid water on Earth, will now be compressed into a tiny region just a few million kilometers from the white dwarf's surface, far closer than Mercury's orbit once was. Any surviving planets will have shifted outward due to the sun's earlier mass loss during its red giant phase. The inner planets, Mercury, Venus, and possibly Earth, will be gone, either engulfed by the sun or destroyed by tidal forces. Mars may still exist, though frozen and lifeless. The gas giants, Jupiter and Saturn, will likely remain, their atmospheres largely unchanged except for gradual cooling. Uranus and Neptune will persist as icy giants, orbiting at even greater distances due to the solar system's gravitational expansion. The outer moons and dwarf planets, once remote and frozen, will be locked in a state of deep cold. Without sunlight, their surfaces will be near absolute zero, with only faint internal heat from radioactive decay or tidal forces, if they orbit close to other bodies, keeping them active. Any brief warmth they experience during the sun's red giant phase will be a distant memory. The debris belts of the solar system will also have been altered. The Kuiper belt may be partially dispersed, with many of its objects ejected into interstellar space. The Oort cloud will still exist in some form, though gravitational nudges from passing stars over the course of billions of years will have stripped away much of its material. The white dwarf itself will be stable, with no further fusion taking place. Its mass will slowly decrease as it emits light and heat, but the process will be incredibly slow. White dwarfs cool over trillions of years. However, it is no longer the center of a vibrant planetary system, but the dim core left after a star's long life. The planetary nebula created during its death throes will have dispersed long ago, enriching the interstellar medium with heavy elements. Those elements, carbon, oxygen, nitrogen, and others, will now be part of new stars and planets forming elsewhere in the galaxy. The Milky Way by this time will not exist in its present form. Billions of years earlier, it will have merged with the Andromeda Galaxy, along with several smaller satellite galaxies. The result, often called Milkomeda, will be a massive elliptical galaxy, lacking the graceful spiral arms that once defined the Milky Way and Andromeda. The merger will have triggered bursts of star formation in its early stages, but by 10 billion years from now, that activity will have slowed dramatically. The supply of cold gas needed to form new stars will be depleted, leaving the galaxy with a steadily aging population of long-lived, dim stars. The night sky, if there were still observers in the solar system, would be dominated not by neat constellations, but by a hazy, uniform glow from the densely packed stars of Milkomeda. Some bright globular clusters and remnants of the original galaxy's cores would stand out. But most of the stars would be faint red dwarfs, their light subtle and subdued. Occasionally, nearby stars might pass close enough to the solar system to disrupt the orbits of its remaining bodies. Such close encounters could send asteroids or comets spiraling toward the white dwarf, producing brief but brilliant flares of light as they are torn apart and heated by its gravity. These events, called tidal disruption flares, would be among the few bursts of activity in an otherwise quiet system. If intelligent life still exists and has remained in or returned to the solar system, it will live under vastly different circumstances. Habitats would need to orbit extremely close to the white dwarf to receive sufficient warmth, or they would have to rely on artificial heat and light sources. Any remnants of humanity or its descendants might maintain the white dwarf as a source of cultural heritage, a monument to their origins, or they might have left entirely, journeying to younger star systems with more stable energy sources. Technological civilizations in this era, if they endure, could be unimaginably advanced. They might have the capability to move entire stars, harvest energy from black holes, or construct structures spanning light years. The physical limitations that once constrained life in the 21st century would be long gone. If such beings remain in the solar system, it would be by choice rather than necessity, perhaps preserving the sun's remnant as a piece of cosmic history. The galaxy itself will be quieter than in earlier epochs. Supernovae will still occur, but far less frequently, as most massive stars will have already burned out. Star formation will be limited to isolated regions where gas clouds remain. The cosmic cycle of stellar birth and death will still continue, but at a pace far slower than in the universe's youth. In this vast timescale, the solar system will have become an ancient relic, a place where the echoes of a once bright star system linger in the form of icy planets, silent moons, and a cooling stellar core. Its history will be written in the scars of impact craters, the drifting orbits of surviving worlds, and the faint glow of the white dwarf. 10 billion years into the future, the fate of the solar system will be sealed. It will remain in this quiet state until the white dwarf fades entirely, unless external forces, such as a passing star, a galactic collision, or the intervention of advanced civilizations, alter its course. Whether it remains a forgotten corner of the galaxy or a preserved monument will depend entirely on the choices of whoever, if anyone, is left to witness it. In the long quiet after the sun's transformation, the remnants of the solar system will continue to drift in their altered orbits. The gravitational bonds between the surviving worlds will be weaker due to the sun's reduced mass, making the entire system more susceptible to disruption from external forces. Passing stars, rogue planets, and even the slow tidal pull of the Milkomeda galaxy's dense stellar environment will occasionally send ripples through the system, changing trajectories in ways that could eject planets entirely into interstellar space. Over a span of billions of years, the orbits of Jupiter and Saturn, if they still exist, may become unstable due to these perturbations. Smaller bodies, such as moons and dwarf planets, will be the most vulnerable, their paths altered until they either collide with larger worlds, are captured into new orbits, or are thrown into the void between stars. Each such event will erase ancient orbital patterns that once defined the solar system, replacing them with new and unpredictable arrangements. The white dwarf itself will be a quiet but relentless beacon of entropy. While it no longer fuses atoms, it will continue to cool and dim, radiating away its stored heat into the universe. This cooling process will take trillions of years, but even at the 10 billion year mark, the white dwarf will be significantly fainter than in its youth. Its light will be stark and bluish when hot, slowly shifting toward red as it loses energy. For any nearby observer, the sun will no longer be a blinding presence but a sharp, hard-edged point in the blackness, beautiful but ghostly. Around the white dwarf, the habitable zone will be so close that any planetary body within it will be subjected to intense tidal forces. Such proximity could rip apart moons or asteroids, forming rings of debris that briefly circle the star before spiraling inward and burning up. These glowing streams of dust and gas will create occasional bursts of light, momentary reminders that the solar system is not entirely static. The galaxy around the solar system will also bear little resemblance to the Milky Way of old. The merger with Andromeda will have scattered stars across vast distances, and many will have been ejected entirely into intergalactic space during gravitational interactions. Milkomeda's core will likely be more active in its earlier post-merger phase, with a supermassive black hole at the center, feeding on streams of gas and emitting powerful jets of radiation. By the 10 billion year mark, however, even this activity may have slowed, leaving behind a stable but aging galactic giant. In the deep cold of interstellar space, relics of the solar system's past may still drift. Spacecraft launched in humanity's early years, Voyager, Pioneer, New Horizons, could still be out there, their electronics long dead, but their metal frames intact. These silent messengers will carry no more than mute testimony to a time when the sun was a bright, life-giving star. Whether they are ever found will depend on whether intelligent beings, human descendants, or alien civilizations continue to explore the galaxy in this far future. If such civilizations do exist, Their technology will be orders of magnitude beyond anything imaginable today. They might harness the rotational energy of black holes, tap into the fabric of space-time for power, or move between galaxies using methods that render the vastness of the cosmos trivial. For them, the solar system may be little more than a historical curiosity, a place to visit not for resources or colonization, but for the significance of what once was. It is equally possible that no such beings will exist. The galaxy may be silent, its civilizations long gone, erased by time, catastrophe, or self-inflicted collapse. In that case, the solar system will be nothing more than a collection of rocks and ice, circling a dying ember in a galaxy indifferent to its history. The memory of Earth and its life will be preserved only in the elemental composition of the dust and gas once scattered from the sun's body into space. The long-term fate of the white dwarf is inexorable. Over the next trillion years, it will cool to the point where it no longer emits visible light, becoming a black dwarf, a cold, dark remnant indistinguishable from the emptiness around it. This is the final step in the life of a star like the Sun, an endpoint where even the residual heat of its birth is gone. In this future, the solar system will be invisible to all but the most advanced instruments, a ghost system hidden in the eternal night. Yet even in this far-off state, the Sun's legacy will endure elsewhere. The atoms forged in its heart, and in the hearts of earlier stars, will live on in other systems, perhaps in alien worlds orbiting younger stars, perhaps in life that arises anew in distant corners of the galaxy. The story of the solar system will not have been wasted. It will have contributed to the ongoing cycle of cosmic creation, as it has since the first atoms condensed in the aftermath of the Big Bang. 10 billion years into the future, the solar system will be a monument to impermanence, a reminder that even stars die, that worlds change, and that nothing in the universe remains untouched by time. Whether or not there are eyes to see it, the fading white dwarf sun will still turn slowly in the void, carrying with it the history of a small blue planet that once knew life, oceans and skies filled with constellations long since forgotten. 100 billion years ahead. 100 billion years into the future, the universe will be deep into a fundamentally different era, an era in which the grand, familiar structure of the cosmos has transformed into something quieter, dimmer, and more isolated. The age of galaxies as we know them will be ending, and the night skies will have lost much of the richness and variety that defined earlier times. For any observers who might exist in this unimaginable future, the universe will look lonelier than ever before. By this point, the accelerated expansion of the universe, driven by dark energy, will have stretched space so drastically that most galaxies beyond our local group will no longer be visible. The light from them will have been redshifted beyond detection, receding faster than it can ever reach us. The great cosmic web of hundreds of billions of galaxies, so prominent in the early universe, will have effectively disappeared from view. Milkomeda, the merged remnant of the Milky Way, and Andromeda will still exist, along with a handful of smaller galaxies bound to it by gravity. These will form an island universe, a lone gravitationally bound structure adrift in an otherwise empty expanse. Beyond this small cluster of stars and dark matter, space will be utterly black, devoid of any trace of the countless galaxies that once surrounded us. Within Milkomeda, the pace of cosmic activity will have slowed to a crawl. The great star-forming regions, nebulae rich in cold hydrogen gas, will have been used up or blown away. Star formation will be rare, limited to occasional bursts triggered by the collision of small gas clouds or the merger of low-mass galaxies. The majority of stars will be dim, long-lived red dwarfs, many of which will continue to burn faintly for trillions of years to come. Massive, short-lived stars will be virtually non-existent. The white dwarf that was once our sun will have cooled substantially by now, fading to a much dimmer glow. Though still radiating heat, it will be so faint that its light will barely illuminate its surroundings. It will have shifted toward the infrared part of the spectrum, invisible to human eyes but detectable with the right instruments. In another few trillion years, it will become a black dwarf, a completely dark and cold stellar corpse. The solar system, if it still exists, will bear little resemblance to the structure it once had. Planetary orbits will have been altered by countless gravitational interactions over the preceding billions of years. Some planets may have been ejected entirely from the system, wandering as rogue planets through interstellar space. The outer reaches of the system may be sparsely populated with ancient comets and icy bodies, though these will be fewer and fewer as passing stars strip them away. Collisions between surviving bodies will be rare but possible, producing brief flashes of light against the darkness. Occasionally, asteroids or comets might be drawn into the white dwarf's gravity, forming a glowing accretion disk as they are torn apart and heated. These events, though fleeting, will be among the last energetic phenomena in the solar system. On the galactic scale, black holes will dominate the centers of what remains of large stellar systems. Milkomeda's central supermassive black hole, likely far larger than it was in our time, will continue to consume any stars or gas clouds that wander too close. Such events will be rare, but when they happen, they will produce some of the last powerful bursts of light and energy in the universe. For any potential civilizations in this era, the universe will be far more challenging to study. Without the light from distant galaxies, the evidence for the Big Bang and the universe's expansion will be hidden. The cosmic microwave background, the faint afterglow of the Big Bang, will be stretched to wavelengths so long that it becomes undetectable by any technology built from known physics. To such observers, the universe might appear static and eternal, its dynamic past lost to time. If life still exists in this era, it will have adapted to extreme scarcity. Energy will be the most precious resource, and civilizations may cluster around the few remaining luminous stars, or extract power directly from black holes via advanced engineering. Artificial structures could harness the Hawking radiation emitted by black holes, converting it into usable energy long after most stars have faded. Such strategies might allow life to persist for trillions of years into the future, though in increasingly isolated pockets. The sky itself will reflect the profound isolation of this epoch. For most of cosmic history, even in sparsely populated regions, the night sky was rich with countless points of light, galaxies, clusters, and nebulae stretching across the heavens. But 100 billion years from now, beyond the handful of stars in the local cluster, there will be nothing but darkness. The observable universe for any inhabitant of this time will be limited to Milkomeda and its satellites, a small cosmic island surrounded by an infinite ocean of emptiness. The long-term fate of this era is predictable: the continued decline of energy, the cooling of stellar remnants, and the gradual fading of the universe's last lights. Yet, in the midst of this vast decline, local activity will still occur. Stars will continue to orbit the galactic center. Planetary systems will still exist around long-lived dwarfs, and gravitational interactions will still shuffle the cosmic deck. The scale of change will simply be slower, stretched over unimaginable timescales. For the descendants of humanity, if any survive, this will be an age of endurance and adaptation. The great epochs of exploration, expansion, and cosmic discovery will be far behind them. Survival will depend on efficient use of dwindling resources, mastery of long-term stability, and perhaps the ability to leave even this island universe for others, if the physics of the future allows for it. From the perspective of the universe's history, the 100 billion year mark is still early in the grand scheme of heat death, the ultimate end when all usable energy is evenly distributed and no further work can be done. But it is already an age defined by isolation, scarcity, and the slow winding down of the cosmic clock. Over the course of the previous tens of billions of years, gravitational interactions will have continued to reshape Milkomeda's structure. Many stars will have drifted away into intergalactic space, becoming part of a thin, invisible halo of wanderers. These lone stars will spend the rest of their lives in solitude, their planets, if any, left in permanent night. The cluster of stars that remains bound to Milkomeda will be a fraction of its former self, its once vast spiral structure now long gone, replaced by a smooth, spheroidal cloud of faint points of light. Within this diminished galaxy, most of the surviving stars will be small red dwarfs. These stars burn their fuel so slowly that they can last for trillions of years, making them the final torches in a darkening cosmos. Around them, Planets may still orbit, warmed enough to support some form of life, though conditions would be starkly different from the warm, bright environments of earlier epochs. Photosynthesis, if it exists at all, would have adapted to the dim red glow of these stars, perhaps relying on different chemical pathways to capture and store energy. Some of these long-lived systems could still be home to thriving civilizations, if they managed to survive the long stretches of cosmic change leading to this point. Such societies would likely be masters of resource efficiency, having developed technologies to recycle matter almost perfectly and harness every photon of light from their host stars. For them, the concept of time would be vastly different. Projects could span millions of years, and change would come so slowly that history itself would feel almost frozen. But beyond these red dwarf oases, the galaxy will be overwhelmingly quiet. Massive stars, supernovae, and star-forming nebulae will have all but vanished. The absence of high-energy processes will make the galaxy appear stable, but also eerily static. Only the occasional interaction between stars, close passes or mergers, will inject bursts of activity into this stillness. The white dwarf that was once the sun will be nearing the end of its visible life. It will radiate only a faint whisper of heat, almost completely cooled compared to its earlier state. Its planets, if any remain, will be silent, frozen worlds drifting in darkness. The slow decay of radioactive elements within these bodies may still provide a trickle of heat, but without sunlight, they will be geological relics rather than dynamic worlds. Black holes will remain among the most significant sources of energy in this age. As matter falls toward their event horizons, it can be converted into radiation with remarkable efficiency. Civilizations, if they exist, might cluster near black holes using their accretion disks or tapping into their rotational energy via advanced methods such as the Penrose process. Even small black holes, formed from stellar remnants, could provide vital power in a universe where most other energy sources have faded. For astronomers in this distant future, understanding the origins of the universe will be far more difficult than it is today. The expansion of the universe will have erased nearly all evidence of its earlier state from direct observation. Distant galaxies will no longer be visible. The cosmic microwave background will be undetectable, and even the large-scale structure of the cosmos will be hidden beyond the cosmic horizon. Without access to these clues, the idea of a hot, dense beginning may be nearly impossible to deduce. In this sense, the inhabitants of this era will live in a universe that hides its own birth. Occasional collisions between smaller galaxies or star clusters within Milkomeda will still occur, but these will be rare and muted compared to the grand galactic mergers of earlier times. The vast majority of stars will drift along stable paths, slowly aging toward the eventual white dwarf stage. The cycle of star birth and death will not have ended entirely, but it will have slowed to a pace that makes each new star a rare and notable event. If humanity's descendants are still here, their cultural and scientific priorities will be profoundly shaped by the conditions of this era. Survival in a resource-poor environment will require unprecedented levels of cooperation, or perhaps absolute mastery over automation and self-sustaining systems. Exploration might turn inward, toward the perfection of life and society, rather than outward toward a universe that offers little beyond the borders of the local cluster. Or perhaps, if they have achieved the ability to manipulate space-time on a fundamental level, they might attempt to escape this cosmic island altogether, venturing into domains beyond the observable horizon. Yet, for all its isolation, this 100 billion-year epoch will not be without beauty. The skies over surviving worlds will be filled with the slow, graceful movement of red dwarfs and ancient white dwarfs. Their light, faint but steady. Black holes will glimmer with the occasional flare of falling matter. And in the far reaches of the cluster, lonely stars will wander eternally, carrying with them whatever history and remnants they once held. 100 billion years from now, the universe will be quieter, darker, and far more limited in scope than it is today. But it will still be a universe, a place where gravity shapes worlds, where matter dances to the rhythms of orbital mechanics, and where life, against all odds, might still find a way to exist in the shrinking pockets of light that remain. For those who endure, the cosmos will be smaller in appearance but infinitely deep in meaning, A reminder that even as the stars fade, the story is never truly over until the last light dies. 1 trillion years into the future. A trillion years into the future, the universe will have entered an epoch unlike anything seen before, a time when the processes that once filled the cosmos with light, heat, and life will have slowed almost to a standstill. The great cycles of stellar birth and death will be all but over. Most of the bright, short-lived stars will have burned out billions of years earlier, leaving behind a universe dominated by faint, long-lived stars and the dark remnants of those that have already died. By this stage, almost every star that could form will have already formed. The vast reservoirs of cold gas that once filled galaxies, fueling the creation of new suns, will have been depleted or locked away in stellar remnants, planets, and other compact objects. The universe will be lit primarily by red dwarfs, the smallest and longest living type of star, capable of burning for trillions of years. These stars, cool and dim compared to the sun, will serve as the last steady sources of starlight. Around them, planets may still orbit, bathed in a soft red glow that barely illuminates their surfaces. Milkomeda, the merged remnant of the Milky Way, and Andromeda will remain the gravitational heart of our local region of space, but it will have changed dramatically. Over the course of hundreds of billions of years, the slow gravitational interactions between its stars will have redistributed energy and altered orbits, causing some stars to be ejected into intergalactic space, while others sink toward the galactic center. The galaxy will appear more diffuse, its core less dense with active stars, and more populated by stellar remnants. White dwarfs, neutron stars, and black holes. The white dwarf that was once our sun will by this point have cooled so far that it no longer emits visible light. It will be a black dwarf, a cold, inert sphere of carbon and oxygen, radiating only faint thermal energy in the infrared. Invisible to the naked eye, it will be detectable only to instruments capable of sensing the faintest whispers of heat. This will be the fate of nearly all stars in the universe, to end as dark, frozen relics, drifting endlessly through space. In the absence of new star formation, the cosmic landscape will be dominated by these remnants. Black holes, formed from the collapse of massive stars or through the merging of smaller ones, will be among the most important players in the universe's long-term evolution. The supermassive black hole at the center of Milkomeda will have consumed countless stars and smaller black holes over the preceding eons, growing even larger and more powerful. Black holes will also represent one of the last remaining sources of usable energy. As matter falls toward their event horizons, it can release enormous amounts of energy, up to 40% of its mass energy, depending on the black hole's spin. Advanced civilizations, if they still exist, may cluster around these cosmic furnaces, building structures to capture and convert this radiation into power. They may even intentionally feed black holes with matter to sustain their output, prolonging their ability to support life and technology in an otherwise darkening universe. But such civilizations would be living in an era of extreme scarcity. Every atom of matter, every photon of energy would be precious. The distances between stars, already vast in earlier epochs, would be effectively unbridgeable for anyone without extraordinary technological capabilities, as most of the remaining stars would be dim and far apart. Even within the same galaxy, the light from one red dwarf to another might take tens or hundreds of years to travel, with the intervening space cold and empty. The cosmic isolation will be absolute beyond the borders of the local group. Thanks to the accelerating expansion of space, no galaxy outside the gravitational bounds of Milkomeda will be visible or reachable. Their light will have redshifted so far into the microwave and radio regions of the spectrum that it will be indistinguishable from the background darkness. To any observers born in this age, the universe will seem to consist solely of their home galaxy, its ancient stars, its black holes, and the slowly cooling remnants of worlds. Within this galaxy, the gravitational interactions of 1 trillion years will have erased most coherent orbital structures. Planetary systems will still exist, but their arrangements may be very different from how they began. Some planets will have been ejected from their orbits, becoming rogue planets drifting through the cold void without a star. Others will orbit white or black dwarfs, neutron stars, or red dwarfs, their surfaces frozen solid unless artificially heated. In this epoch, geological processes on most planets will have ceased entirely. Without significant internal heat from radioactive decay, which will have run its course over billions of years, planetary interiors will be cold and inert. Tectonic activity will have stopped, magnetic fields will have vanished, and atmospheres, if any remain, will be thin and frozen. The only geologically active worlds will be those close enough to massive bodies to experience tidal heating, moons orbiting giant planets, or binary systems where gravitational forces still flex and warm their interiors. If life survives into this era, it will bear little resemblance to what we know. It may be entirely artificial, existing in engineered habitats powered by black holes, nuclear fusion reactors, or the slow decay of exotic particles. Biological life, if it persists at all, will likely be confined to environments carefully maintained by intelligent beings. The conditions for spontaneous life to arise naturally will be nearly non-existent, given the scarcity of energy and the absence of warm, wet worlds. The ultimate fate of the universe is still far off at this point. But the heat death, a state in which all usable energy is evenly distributed and no work can be done, is already on the horizon. Every star that dies brings the cosmos closer to that equilibrium. Every black hole that evaporates through Hawking radiation, a process that takes unimaginably long time scales, moves the universe toward a state of total uniformity. And yet, even in this dark and distant era, beauty will remain. The red dwarfs will still cast their gentle light on ancient planets. Black holes will still flare occasionally as they consume matter. And the gravitational ballet of surviving worlds will continue. The scale of change will be slower than ever before, measured not in millions or billions of years, but in spans so long they defy ordinary comprehension. 1 trillion years from now, the universe will be quiet, sparse, and cold, but it will still be here, still evolving, still carrying forward the remnants of everything that came before. In the grand perspective of time, it will be just another chapter in an endless story, one where light has dimmed but not yet gone out completely. Over the previous trillion years, gravitational interactions will have relentlessly reshaped what remains of the galaxy. Stars will have exchanged orbital energy, slowly migrating inward or outward. Some will have been captured by massive objects, spiraling toward their destruction, while others will have been flung entirely out of Milkomeda, left to drift eternally through intergalactic space. These exiles, rogue stars carrying any surviving planets, will travel alone in darkness, their faint light wasted on the void. In the central regions of the galaxy, the supermassive black hole will remain the dominant force. By this time, it may have grown to tens of billions of solar masses, swallowing countless stars, gas clouds, and smaller black holes over the preceding eons. Every so often, a surviving star or remnant will wander too close, torn apart by tidal forces in a final, brilliant flare that lights up the galaxy before fading into silence once more. Around smaller black holes scattered throughout the galaxy, remnants of civilizations, if they still exist, may cluster, harvesting energy from accretion disks or Hawking radiation. In this dark age, black holes are more than just cosmic graveyards. They are power stations. Their slow but steady energy release perhaps the only means of sustaining advanced life. For those who have mastered the physics of this era, feeding black holes with captured matter might become a deliberate strategy, extending the availability of energy far beyond what stars alone could provide. The remaining red dwarfs, though still burning, will be nearing the limits of their fuel supply. 1 trillion years is a long time even for these frugal stars, and many will now be transitioning into white dwarfs themselves. This gradual decline will steadily shrink the number of active light sources, pushing the universe closer to its final darkness. Around some of these fading stars, planets will still cling to their orbits, frozen except in the narrow habitable zones near the star. In many cases, these zones will be so close to the stellar surface that any planets within them will be tidally locked, one side in eternal daylight, the other in endless night. The black dwarf that was once the sun will be a silent witness to all of this. Completely invisible without specialized instruments, it will drift through its orbit, assuming it has not been ejected by gravitational interactions, around the center of Milkomeda. Its surface temperature will be only a few degrees above absolute zero, its last thermal energy slowly radiating away over unimaginable timescales. Any planets that remain bound to it will be equally frozen, their surfaces buried under thick layers of ice and dust, their atmospheres long gone to space. The distances between the few remaining pockets of light will be vast. For any civilization, travel between star systems will require staggering amounts of time or the ability to manipulate space-time itself. Without faster-than-light travel, if such a thing is even possible, societies will be isolated on a scale far beyond anything in earlier cosmic history. Communication between them will be limited to the nearest neighbors, if at all, and cultural exchange may be non-existent. For observers in this epoch, the history of the universe will be largely inaccessible. The clues we rely on today, light from distant galaxies, the cosmic microwave background, will be gone, erased by expansion and redshift. Without a deep scientific record preserved from earlier times, the inhabitants of this age may have no way of knowing the true origins of their cosmos. They could live in a universe that appears static, infinite, and eternal, unaware of the Big Bang that began it all. Still, the universe will not be entirely without motion or change. Gravitational encounters will continue to shift orbits, occasionally sending planets or small bodies into collisions. Though such events will be rare, their energy releases will stand out dramatically in the quiet darkness, creating temporary bursts of light visible for light years. Over even longer spans, gravitational radiation from binary systems will cause them to slowly spiral together, releasing faint waves that ripple through space-time. The fate of any remaining life will depend entirely on its adaptability. Biological organisms, if they persist at all, will have to survive in carefully engineered environments, perhaps orbiting close to low-energy stars or black holes. More likely, intelligence in this age will be entirely post-biological, machines, information systems, or entities existing in substrates optimized for minimal energy consumption. Such beings could slow their subjective experience of time to match the slow pace of cosmic events, living for what, to them, might feel like eternity. And yet, even for these long-lived intelligences, the universe will eventually present an unsolvable problem. All available energy sources will run down. The red dwarfs will go dark. The white dwarfs will cool into black dwarfs, and black holes will begin the long process of evaporation through Hawking radiation. While the evaporation of a supermassive black hole will take vastly longer than 1 trillion years, closer to 10 to the power of 67 years, it will still be inevitable. When it happens, it will be one of the last bright events in the universe, a final blaze before the lights go out for good. 1 trillion years from now, the cosmos will be profoundly different from the vibrant, galaxy-filled universe of its youth. It will be a place of isolation, scarcity, and slow decay, where change is measured not in centuries or millennia, but in spans so long they challenge the very concept of time. And yet, it will still be a universe, still shaped by gravity, still home to motion and transformation, still a vast stage for the remnants of matter and energy to play out the final acts of a story, billions of years in the making. Beyond 1 trillion years, when the universe moves beyond the trillion-year mark, it will be deep into what astrophysicists call the degenerate era, a time when the familiar structures and processes of earlier cosmic ages have largely ended. The great epochs of stellar birth and death will be over, and the cosmos will be dominated not by shining stars, but by the dark, cold remnants of what once was. The universe of this era will be composed almost entirely of stellar corpses, black dwarfs, neutron stars, and black holes. Red dwarfs, the longest-lived stars, will have finally exhausted their fuel, fading into black dwarfs themselves. White dwarfs, remnants of more massive stars, will have cooled to near absolute zero. Neutron stars will remain as incredibly dense, city-sized spheres, though without the radiation they once emitted. Galaxies, if they can still be called that, will be faint and diffuse collections of these remnants, bound together loosely by gravity. Over time, even these structures will thin out, as gravitational interactions gradually eject objects into intergalactic space. The mergers and collisions that once shaped galaxies will become exceedingly rare, occurring only when the slow drift of remnants brings them close enough to interact. The universe's dark energy-driven expansion will have carried all but the closest gravitationally bound structures far beyond each other's reach. The local group, or whatever remains of it, will be an isolated island of matter surrounded by an endless expanse of darkness. No light from beyond this island will ever reach it again. The rest of the universe will be forever inaccessible. Black holes, which formed in great numbers in earlier cosmic epochs, will still be present in large quantities. Supermassive black holes, in particular, will dominate the cores of whatever remains of former galaxies. For trillions upon trillions of years, they will be the most significant sources of high-energy phenomena, as they consume the occasional remnant star, rogue planet, or gas cloud. The infall of such matter will release brief bursts of light and radiation, standing out starkly against the universal darkness. However, even black holes are not eternal. According to quantum theory, they slowly lose mass through Hawking radiation, a process in which quantum effects near the event horizon cause particles to escape. For small black holes, this evaporation happens relatively quickly by cosmic standards. But for supermassive black holes, the process takes incomprehensibly long timescales, up to 10 to the 67th years or more. Still, in the infinite patience of the cosmos, this is merely another step toward its final state. In this far future, energy scarcity will be the defining challenge for any form of life or intelligence that still exists. Stars will no longer provide steady, abundant light and heat. Civilizations, if they persist, will have to find ways to extract energy from the rare and fleeting events that still release it. This could mean living in orbit around black holes to harvest their Hawking radiation, tapping into the decay of exotic particles, or building massive structures to collect the faint heat emitted by cooling black dwarfs. It is likely that if intelligence still exists at this stage, it will no longer be biological in the way we understand it. The slow pace of change and the extreme scarcity of resources favor life that can minimize energy consumption and survive for vast stretches of time without activity. Advanced civilizations might adopt stasis strategies, slowing their subjective experience of time so that they only wake for short periods every million years, using minimal energy while they sleep through the cold darkness. Rogue planets and other free-floating bodies will drift endlessly through the void. Many will have been ejected from their parent systems long ago. These wanderers will be frozen solid, their interiors possibly retaining faint geothermal warmth for trillions of years longer. Some could host subsurface oceans maintained by radioactive decay or tidal heating if they remain bound to a massive object. Such worlds might harbor isolated pockets of microbial life, the last biological survivors of the universe. As time stretches onward, the population of active astronomical objects will continue to decline. Each black hole that evaporates, each neutron star that cools, and each black dwarf that fades will bring the universe closer to a state of complete thermodynamic equilibrium, the so-called heat death. In this ultimate condition, all matter and energy will be evenly distributed, and no work will be possible. Before that final silence, however, the degenerate remnants will still occasionally interact. Binary systems of black dwarfs, neutron stars, or black holes will slowly spiral together due to the emission of gravitational waves, merging in spectacular bursts of energy. These events will become rarer as time passes, but each will stand as a momentary flash of brilliance in an otherwise unchanging universe. On timescales far beyond even 1 trillion years, the fate of matter itself comes into question. If protons are unstable, a possibility suggested by some grand unified theories, then they will eventually decay into lighter particles, such as positrons and neutrinos. This process would transform all matter into radiation over spans of 10 to the 34th to 10 to the 40th years. If proton decay occurs, then every planet, star, and remnant in the universe will ultimately dissolve into a thin mist of subatomic particles. If, on the other hand, protons are stable, then matter will persist indefinitely in the form of degenerate remnants. In such a universe, the final transformation will be slower, as black holes evaporate and the last solid objects drift endlessly through the cold void. Eventually, even atomic motion will cease, and the cosmos will approach a deep freeze in which nothing changes. In either scenario, the post-trillion-year universe will be a place of extreme simplicity. The complex structures of earlier epochs, galaxies, solar systems, biospheres, will be gone, replaced by a sparse scattering of slowly moving relics. The vast dynamic universe of stars and nebulae will be only a memory, preserved perhaps in the data archives of civilizations long vanished. Yet, even in this quiet, there will be a certain grandeur. The universe will not have ended violently in a single cataclysm, but will instead have faded gently into darkness, each stage of its decline lasting longer than all of human history, many trillions of times over. For those who can endure into this age, the cosmos will still be a place of motion, however slow, of light, however faint, and of meaning, however abstract. Beyond 1 trillion years, time becomes less a measure of events and more a canvas of stillness. The great drama of the universe will have played out, leaving behind a stage where only the faintest actors remain, performing for no audience but themselves. The gradual fading of the universe will be measured in spans so vast that the human mind, shaped to think in seconds and years, can scarcely grasp them. At this stage, the distinction between soon and later will lose meaning. Cosmic change will unfold at a pace where 1 billion years passes like the blink of an eye. The universe's clock will tick more slowly, not because time itself has changed, but because so little is left to happen. The large-scale structure of space will be almost featureless. Every gravitationally bound group of remnants will be a lonely island, cut off from all others by the accelerating expansion. Between these islands, there will be nothing. No light, no matter, no possibility of travel or contact. The only interactions will occur inside these final clusters, and even those will grow increasingly rare. In some systems, pairs of black dwarfs, or neutron stars, will continue to spiral together, their orbits shrinking over unimaginable timescales through the slow leakage of gravitational waves. When they finally merge, the collision will release a burst of energy, an echo of the violent past of the universe. These events will stand out as singular beacons in an otherwise static cosmos, momentarily illuminating the darkness before fading again into stillness. Black holes, those great anchors of the cosmos, will endure far longer than any other structure. They will continue to shape the motions of surrounding remnants, occasionally consuming them in bright flashes. Yet their reign, too, will come to an end. Hawking radiation will eventually cause them to shrink, grow hotter, and finally evaporate in a spectacular release of energy. For a stellar mass black hole, this process will take around 10 to the 64 years. For a supermassive black hole, it could take up to 10 to the 100 years or more. The final moments of these titans will be among the last luminous events in the universe. For any remaining civilizations, if the term still applies, they will live on the edge of energy bankruptcy. They will need to extract every possible jewel from every possible source, using technologies incomprehensible to early humanity. These beings may no longer be made of biological tissue, but of highly efficient, self-repairing materials or patterns of information existing in ultra-cold computational substrates. Their existence will likely be punctuated by long periods of dormancy, waking only when significant cosmic events occur, such as the approach of a merging binary or the evaporation of a black hole. Such civilizations may also dedicate themselves to preservation rather than expansion. Without new energy or resources from beyond their gravitational island, survival will mean maintaining what they have for as long as possible. They may build colossal data archives, preserving records of the universe's vibrant youth for future intelligences that may never come. They might create artificial suns by carefully feeding matter into small black holes, regulating the energy output over trillions of years. Or they could migrate slowly inward toward the last gravitational wells, eking out the final scraps of energy before darkness claims everything. If proton decay is real, this will mark the ultimate limit for matter. Over timescales of at least 10 to the 34th years, every proton in the universe will eventually transform into lighter particles, leaving nothing but radiation. Structures from planets to people will vanish into a sea of subatomic debris. In such a universe, only black holes will remain for a time until they too evaporate. Once the last black hole is gone, the universe will enter the dark era, a period where only low-energy photons, neutrinos, and other elementary particles drift through an unimaginably vast, cold space. If protons are stable, the end will be slower but equally final. Black dwarfs will persist indefinitely, though their temperatures will hover just above absolute zero. The cosmos will be a graveyard of these frozen remnants, along with neutron stars and black holes, all separated by unimaginable distances. Gravity will still operate, but without energy gradients to drive change, the universe will move ever closer to thermodynamic equilibrium. Heat, death. In either case, the story ends not with a bang, but with an eternal fade. The complexity of the early universe, galaxies, stars, planets, life, will give way to a simple, cold uniformity. Motion will persist, but without energy differentials, nothing new can form. Nothing complex can be sustained. Yet there is a kind of majesty in this ending. The universe will not have been destroyed. It will simply have run its course, like a great fire that has consumed all its fuel. Its ashes will be scattered across an infinite stage, still bound by the same fundamental laws that guided the birth of stars and the dance of galaxies. The physics will be unchanged. The actors will simply have left the stage. If there are any witnesses left, perhaps a lone intelligence orbiting a fading black dwarf, or a machine intelligence sleeping between millennia, they will see a universe that is quiet, stable, and almost serene. Every particle, every bit of energy will be in its place, and though there will be no more life, no more light, the memory of the cosmos' glorious past will remain encoded in the matter and space that once carried it. Beyond 1 trillion years, the universe will be ancient beyond reckoning. And yet, in the sheer vastness of its timescales, this will only be one more chapter, an almost infinite stillness stretching ahead, waiting for nothing, ending in nothing, but existing all the same. I hope you enjoyed this journey through the endless timeline of the universe. If you're still awake, you can find another relaxing cosmic journey right here on the screen that will take you to even more wonders of space and time. Until next time, sleep well and keep looking up.